Okay. No, the other one. Okay, so sorry for the delay. I talked to a colleague about some study programs and about the strategies for the future. And yeah, so today it's about in-database machine learning. So actually this is kind of my research topic. So I'm doing two things. Like one thing was about versioning. How can we integrate version control inside of database systems? And the other idea of mine is how can we integrate machine learning with database systems? Like big data, so like currently with big data, where is the data stored? The data is of course stored in database systems. And therefore my research aims to eliminate any extract, transform, load process. So the idea is we have the database system storing all the data, then we have to extract it with some Python scripts, and then we can manually have some Python script that do all the machine learning and data mining on it. And I try to eliminate this. So actually this is my research, and therefore I have this chapter on in-database machine learning. So what I'm going to talk about is, first I want to show you some data mining algorithms. Then I will show you how data mining algorithms can be done in SQL. So with all the SQL knowledge you have, how can we code those data mining algorithms? And then I will go on about machine learning, so some basic things about automatic differentiation and gradient descent. And then I will show you how I actually implemented this in SQL. Last but not least, I will show you some data representations you use normally in machine learning, and then how this can be done inside of database systems. So today it's all about the connection between machine learning and database systems. Okay, so I wanted to start with some data mining algorithm. And like the most popular data mining algorithm is clustering. So I'm not sure how many have heard about k-means. After half, that's great. And I will show you how this can be done in SQL. So the idea, okay, we have clustering algorithms. So we can see we have some points. So this is, for example, a database table. And then now the question is, how can we arrange those points together? And the idea is, okay, by just looking onto it, we can see we have maybe 3 clusters. So, okay, and how do we get these clusters? So k-means basically is named k-means because it has k clusters. So in the beginning you specify how many clusters you have at the end. So therefore you start with k arbitrary random points. These k arbitrary random points form the initial centers. Then you want to assign each point to the center that is the closest. Afterwards, you compute the new centers as the middle of each center. And you do that until it either converges or if it might never terminate, you have to set a point, a limit after what you do not want to continue. So either after an iteration limit or when it converges. Okay, so let's do it with an example. So here I have my points. And what do we select? Randomly we say, okay, we want one center with A, one center with B, and one center with H. And then, so these are our 3 clusters. And then we can say, okay, which are the ones which are the closest? And so the next one would be C. Okay, C is the closest to B. Then D also is the closest to B. E also. So we know that these 4 points belong to B. So then for H, we see that F and G are the closest. So F and G and H all belong to the cluster with H. And finally, R forms a cluster on its own. So then we have to recompute the new centers. It's just the middle of all points. So this is the one cluster, the middle is located here. Here we have the other cluster, which only consists of 1 point. So this is also, the old center is also the new one. And here we take the middle out of these 3 points. So this is the first iteration for k-means. So let's formalize this a bit. So we would say we have n-dimensional points. So in the example we had 2 dimensions. So here in this example we have 2 dimensions, and how many points? 1, 2, 3, 4, 5, 6, 7, 8 points. Then we have some initial centers, and the centers are apart from the original points. So here our initial centers is a subset of the set of all points. And then for distance we can use, for example, Euclidean distance. So this is just a normal a square plus b, so the square root of a square plus b square. So here we see a square plus b square, and then we take the square root. So this is the distance function we use for here. So this is called Euclidean distance. And then we assign the points to the next center. And actually this is a trick, because I want to show you how this works in SQL. So it's a bit of crazy, but I liked it, and it's just to see how powerful SQL actually is. So I said, okay, how can we assign a point to the closest center? So a point belongs to a center if there are no other center exists which is closer. So this formula actually gives you all the points for a cluster. So this is the cluster C. So if you say, okay, we have the first one here, we get all the points belonging to this center. So a point belongs to the center. So a point belongs to the center if there no exists any other cluster which is closer. So this was my trick to model k-means in SQL. Yeah, so basically that's it. One function that returns you all the points to a cluster, and then recomputing the new centers is quite easy. Okay, and yeah, I wanted to do that in SQL. And so let's start with SQL. So first we can model our points in SQL just using a CTE. So here we have our points, and then we have all the values. Yeah, quite easy. Then in the next step, okay, we want to say we have our initial centers, and this again we can model this with a CTE. And now the hard tricky part, we need a function that returns all the clusters. And that's what we do. Here we say, okay, we want all clusters for which not exists a cluster that is closer. So it does not exist another cluster that is closer to the one. And then, okay, I say, okay, the minimum CID, so then I used an aggregate function by the actual point coordinates. And then I used here a cluster ID, and the cluster ID, where does it come from? Yeah, and I here what first cluster, second cluster, third cluster. Therefore, if one point is beneath 2, I'm using the one which is lexicographically closer. So I assign every point to a cluster. Actually, this is a join where not exists a cluster that is closer. And therefore, I'm assigning each point to a cluster. So that was my trick to model k-means with SQL. And then I have to recompute all the middles. And this can be done, okay, I have to average the x coordinates and the y coordinates, and then I have the inner formula from above. And then I have the new middles, and this can be put into a big recursive table. So here I have my clusters and I have my iterations until which I will stop. And here I will recompute my new centers. And I terminate after 100 iterations. So you can see that it is possible to model k-means also in SQL, although it might not be fast as it should, but you can see how powerful SQL is. Yeah, so actually for the exam I'm not expecting big statements. It will be more basic, but I have prepared this slide, and actually it's a bit of my research, so I wanted to show you how it works. So you see how powerful it is, and actually for the homework, I think one homework is about doing DB scan in SQL. It's another clustering algorithm. So it's also a trick like that. And actually I'm really eager to do a lot of things in SQL and find smart and fast solutions using aggregate functions. And I want to teach you and train you to do a lot of things as much as can be done in SQL. Yeah. Questions, by the way? Yeah.
So during the example that you gave, you had like data points, and you can measure the distance between the two. But
Yeah.
if you have like for example tables, do you map those into a two-dimensional diagram, graph, and then you use the algorithm? For example, if you have all
So I
attributes,
think the
name and
short
surname,
answer.
how can you measure the distance?
Sorry?
If you have attributes, for example, from a student in a table, name and surname, how can you measure the distance?
But you want to measure the distance? But so the question is, why do you want to cluster by name? So then it would be lexicographically clustering, right?
Yes.
But you can map actually every character.
To 2D-dimensional space, and then you can use the
So like the two dimensions in your case are the names, prename and surname, I guess. And then by actually characters, so strings, are also just numbers. It's also just bits and bytes. Actually, of course, you have a mapping between names and numbers. Yes, you need a mapping, but it would be quite easy because like every character actually is kind of a number. It's also just bits and bytes, but of course you need a mapping. Okay, k-means minimizes distance to center points. That's the idea. It's easy to implement, but ignores outliers, and the number of centers is predetermined. Do you know other clustering algorithms? No one? KAN, K nearest neighbor. Yeah. Would be one possibility, yeah. Yeah, but actually support vector machines, I think they have only two dimensions. So like they have one kind of a line and then they assign.
It can be also multiple dimensions, and then you draw like
yes, it can.
Into between the dimensions. And you first need to measure the distance between the data points,
Mm-hmm.
then you can draw it like
Yeah.
by picking the mean or the average between the
Yeah, I remember 2 years ago, I was talking about support vector machines, but not this year, I'm sorry. So you have ideas in the last row? No?
random forest.
Random forest is it's a good point. Normally I forgot to include decision trees. It's a good point. Yeah, so actually random forest is just multiple decision trees. Like it's not really clustering, it's just decision trees. Yeah?
Like where every data point is a cluster, and then you work through them.
So I want to show you, I have prepared another one. And actually the one I want to show you works like that you said, but it's called differently. So I'm not sure what you mean. So I know one clustering algorithm that starts by every point is a single cluster and then I merge. But I have a different name for it. So it would be interesting. So let's Google it. Hierarchical clustering.
It is important.
So it exists. So we can have a look here. Mm-hmm. Okay, good. So yeah, normally I have one chapter about data warehousing where I was discussing about decision trees, but not this year. I forgot to talk about decision trees. What I wanted to talk about is Dbscan, and like this is like the one which is the big competitor of k-means, because in difference to k-means, Dbscan first can deal with noise. So if a point doesn't belong to a cluster, if a point is an outlier, it's declared as noise. And also, like, the number of clusters is not predetermined. I say, okay, I have only 2 parameters. Like the first one is the first number is for the distance, and the second number is the number of points that must be part of a cluster. Otherwise, the whole cluster or all the points within a cluster are declared as noise. And it works like every point initially is a single cluster, and then we merge clusters that are less than epsilon away. And we repeat this until we have not found any new cluster. And afterwards, we can check. We count the number of points in each cluster, and if it's less than min points, then we say, okay, the points are marked as noise. And like this was the big algorithm of Hans-Peter Kriegel, so it was at LMU Munich from the group, and like this is the big alternative, the popular alternative to k-means. So the idea is, so we start, like in the beginning, we say, okay, we have one cluster for every point. So like here in the first iteration, we have the clusters. Okay, and then in the next, we merge. So we measure whether this is less than epsilon. So we should have specified an epsilon. So and if this is the case, in the next, we merge those clusters. So we say, okay, CDE forms one cluster for its own. So we have one cluster containing those 3 points. Then we also have to look whether whether the distance here is less than epsilon, and also this one, and also this one. So, and of course we could try to compute this. So here, what do we have? A and B is exactly 2. Like here, F and G, F is 8 and 9, and G is 10 and 8. So we have 10 minus 8 plus, and I think square, plus, what is the other? Okay, it's just 1. And actually we have to take the square root, and this would be 2 to the power of 2, so 5. And actually we would need the square root of that. Also we can compute this distance, and this is actually H and G. So those, it would be 12 minus 10 square plus 10 minus 8 square, and this would be 4 plus 4 would be 8. So for example, if we would say, okay, epsilon should be, let's say, something smaller than the square root of 8. Then we would say, okay, H is not part of this cluster, still forms its own cluster, but those two are merged. So then we can say, okay, F and G are in the same cluster, H isn't. And here A and B, of course, would be in the same. So then we can see we would have 1, 2, 3, 4 clusters, and then we have the other point for other number, which would be called min points. If this would be equal to 2, then all clusters with less than 2 points is noise. So we would say, okay, at the end we only have 2 clusters, A and B, C, D, E, F and G, and H would be noise. And that's actually how dbScan works. Yes?
Why H wasn't in class?
Sorry?
Why H wasn't in
So the question is, how much is the distance? Like we have the distance here in between, and like we have the factor, so epsilon, and epsilon specifies the distance between 2 points to form a cluster. And if we choose an epsilon now that H is farther away, so the distance between H and G is larger than this epsilon, then it won't be part of the cluster anymore. That's the idea. Yeah.
But if it's noise, it probably gets included in the cluster next to it, right? So it would probably be in FP cluster.
So if it's declared noise,
So, yeah, if it's declared noise, then it will be removed or added to the cluster?
it will be removed.
Okay.
Noise is removed, yes. It's like the idea we have a lot of data points and everything else is an outlier, is like an error in the measurements or something like that. So it will be removed, yes. So this will be your homework to do this in SQL. So actually I did it and I also published it, and the idea was, okay, I'm using the minimum, so I'll take the point ID as number, as cluster number, and I'm recursively recomputing all the clusters, and I take the minimum of the points, and then I say, okay, so I have an aggregate function, and I aggregate by the distance, and then I take the minimum, lexicographically minimum string as cluster center. Yeah. But I wanted to show you dbScan because no one taught it to me when I was a student, and like these are the most two important clustering algorithms I know, k-means and dbScan. Yeah. And now you know. But actually for the exam I will be happy if you know about basic SQL, basic CTEs, and this is just one example how we can use it, and also I hope if I teach you all the machine learning things, and sometimes I need students doing the machine learning stuff, so I think if you have heard it you might know it for a thesis afterwards. So that's also what I have in mind when teaching this. Okay, so much about data mining. So let's talk about machine learning. And basically if you have in machine learning, so basically what you do, you have a loss function, and the idea is okay, you have somehow linear regression, for example, like you have you have points, and you want, so linear regression is just drawing a line. So you have two parameters. The first one is the offset. So here it's the b, and we have the what is it? The parameter, the factor on the other side. That's the a. So this is the a. So and the idea is, okay, we want so actually for linear regression there's a numerical solution. You do not need to do gradient descent, but the idea is, okay, I want to get these parameters using gradient descent. And the idea is, like in machine learning, we never look for the optimal solution. We try to approximate it using an iterative algorithm. So the idea is, okay, I actually have my optimal line. And before that, I try to try with another line, and then I want to measure how much is the difference. And the difference is actually the loss. And that's basically the idea in machine learning. I'm looking for an optimal solution. I don't compute it, the optimal one. Instead, I try to approximate it iteratively. Okay, and basically that's the example here. I have a model, and the model here is, for this example, just linear regression. So it's just a line. And for every point, I have my optimal point. So the y, these are the breadpoints. So I have, of course, my x-axis and my y-axis. And for every point here, for every x, I have also my y. And the idea is to find the closest line. So the idea is, my line here should be on the same, all the points should be located in the line. So the idea at the end is all the points. So this, so the distance from the points to the line should be minimal. So this distance and this distance should be minimal. So if I have my line here, so x and y, and the idea is all the points here, so this distance and this distance should be minimal. So that's the idea. And the sum of all the distances here actually is the loss. So for every single point, and then the idea for the total loss is actually the sum of all points. So of all x, so here, this would be the total loss. Okay, so model function, the idea is a line to approximate each y, and then the loss basically is the distance. The distance between my model I found and the actual points I have. That's called loss. So actually, here, the total loss would be the sum of all points. Okay, so loss is just the difference. Okay, and then the idea is, how can we get this? We can say, okay, we find the minimum by moving in the deepest descent. Like this loss function, if I model this loss function, you see we have mean squared. So mean squared means we have a squared function. And then the idea is, okay, this function has a minimum. And this minimum is somewhere located. And we have to find it by moving in the deepest descent. And that's the idea. And we get the deepest descent, like the deepest descent is just the derivative. So we move into the opposite direction of the derivative. And the derivative for a multidimensional function is actually the gradient. So we say, okay, to find the minimum, we have to move into the deepest descent, and therefore we have to take the derivatives for each dimension. So the two dimensions are a and b that want to be optimized for, and therefore we have to derive once with regard to a and once with regard to b. So the loss function derived with regard to B and to A. Okay, so that's the deepest descent, that's the gradient. And then what we do in each iteration, we compute the difference like we move one step. Okay, so that's actually gradient descent. So far it's clear for everyone, isn't it? And now the idea, I wanted to, so actually the idea was, okay, I talked to one who was researching on graph machine learning, and I wanted to know him, what do you need for a database to do all your stuff inside of database system? And then he said, we need arrays and we need gradient descent. And then the idea was, okay, what do I need for gradient descent? And the idea is actually SQL is Turing complete, so I can do everything with SQL for gradient descent. And the idea is, okay, I have my data points, x and y, and then I have my recursive function. And like in the first step, in my first iteration, iteration 0, I start with an arbitrary weight. So I take, for A I take 1, and for B, for the offset, I also take 1. And then for every iteration, I update the weights, like A and B, by subtracting the derivative. And the derivative is once derived with regard to A, once derived with regard to B, so once with regard to A here, and once with regard to B. And I do this step for step, and therefore I have a factor, and the 0.05, it's actually called the learning rate. Okay, and then I have my new weights, and I can do this as many steps as I want. In this example, for example, 5 steps. And this would be gradient descent in SQL. And yeah, so actually machine learning, what you can do is you can first create the distance and the difference of the distance for every point. So it actually take the sum of all, and that's what we do here. Basically we take the sum of all. So basically I'm using here an average quite simply because like actually I'm using the sum divided through the number of points. And instead of having the sum and then dividing through the number of points, I'm just using the average. Instead, you could also use sum as aggregate function using a smaller learning rate. So you see, taking all the points here, the sum, the total loss, you want to compute the gradient for all points, then you take the sum. As here you see, we take the whole table. Okay, and then the idea is this is called batch gradient descent. So now you have seen batch gradient descent in SQL, taking all the numbers. And then actually what they do in machine learning, they just use a single tuple. Do you know things of getting only a single tuple from a table? Some statements you have seen already. So there's a function called sampling. So here it's called table sample. If you remember, we had Bernoulli distribution. Bernoulli was like taking a certain number of percent, and with reservoir sampling you get exactly one tuple. And for example with this, you only get one tuple. So table sample reservoir just extracts you one tuple, and having only one tuple for learning is called stochastic gradient descent. And instead you can also take more than one tuple, and here if you're taking more than one tuple, so actually here would be an 8, you can't see it anymore, I'm sorry, and this would be called mini batch gradient descent. So stochastic gradient descent means you'd randomly take one tuple for one step. Batch gradient descent means you take all the tuples, and mini batch you take a few tuples. So now you know how gradient descent actually works, and you know the difference between stochastic gradient descent, batch gradient descent, and mini batch gradient descent. And I think using table samples it's actually a quite elegant solution, isn't it? And then there was something I was really investigating, like you see we all did the derivatives manually. You see? And then the question was, can we do it automatically? Like the more complex a function is, the more complex the derivatives get. And then I was investigating into automatic differentiation. And so the next goal is about how can we do this automatically, so that you do not need to hand write the derivatives anymore. And this is called automatic differentiation. So actually, if you know anyone in machine learning, and all the people who are doing machine learning basically need the derivatives, and okay, most of the times it's just mean squared error, and like deriving mean squared error always results in a function like this, taking the original one times the variable. But actually I wanted also to derive more complex functions. And you should know, actually you can derive symbolically. That's how you learned it in school, or maybe in the analysis class, pen and paper. You can write it down, you have your rules, but then you need to compute it for every single variable again. And therefore there's a technique called automatic differentiation. And the idea is, if we have a function f of g of x derived with regard to x, then we can say, okay, we have two derivatives. We have f with regard to g, and we have g with regard to x. And then the idea is, okay, we first compute one direction, the first one, and then we use the second one. And that's actually automatic differentiation. We have like all the expressions, all the partial expressions are derived once for once. So we have for every partial expression we have one partial derivative. And the difference now is, what do we compute first? Do we first compute the inner derivative or the outer one? And if we compute first the inner one, this is called forward mode. And if we first compute the outer one, this is called reverse mode. And yeah, like here you see the difference. And for the forward mode means, okay, so here you see the first term, that is just the function evaluation. So x, then we have g of x and y, and then we have f dependent on g, dependent on x and y. And so the first term is just the evaluation of the result. And then we have the second term, and the second term is just the derivative. And we start like we want to derive the whole function with regard to x. So we start by the partial expression is x, so the partial derivative x with regard to x is 1. And then we have to propagate this, like now here belongs the derivative of g with regard to x, and then we can reuse this term. Here you can see we reused it for the whole derivative. So f with regard to x is a derivative of f with regard to g times the g with regard to x. So that's forward mode. And the other mode would be reverse mode, and then we start in the other direction. Yeah, so this is automatic differentiation basically. And now, like the problem is, for the forward mode, we can do it in one pass. So you can see we evaluate the function and we compute the derivatives. So one pass only. So it's like memory optimal, because like for a bigger function we can forget all the previous results. Like we do not need, if once we have computed this derivative, we can forget the old results. So I only need one pass. But the problem is, in the beginning we have to determine to which variable we're using for the derivations. So here, for example, we have to first derive with regard to x, and then if we want to get derivatives with regard to y, we have to redo all the steps. Because like here, for y with regard to x is always 0, and if we want to compute the whole function, if we want to derive the whole function with regard to y, we have to recompute it. And that's why most of the times reverse mode is used, because like this computes the derivatives for each independent input variable in one pass. But we need two passes, we need one forward and one reverse pass. So do not get confused, in reverse mode we have two passes, like the forward and the backward, and in forward mode we have only one pass. Okay, so much about introduction to automatic differentiation. Let's have an example. So basically the example is always like we have one function, so you see this function x plus y times z. So reverse mode means we first have the forward pass. Forward pass means just computing the function. And then we can compute the derivatives. And we start by the outer one, and the outer one is of course f derived to f, and this is always 1. So that's why we start with 1. So we propagate this partial derivative to the next partial expressions. So here we have the partial derivative of the previous one, which now might be used for the next one. And the next one is just x, so is of course the whole expression, this whole expression derived to z. Okay, so this actually is x plus y, 5. Okay, let's take the other side. So this actually is just 6, and then we can make use of the chain rule, because now we have like the previous one, and now we only need to derive the inner part. So what we do now is just deriving the inner part, so this one. So here we are just deriving the inner part anymore. So we're deriving x plus y with regard to x, and using the previous previous value as seed. So we only have to derive x plus y with regard to x times the previous partial derivative, and then at the end we get the whole function derived with regard to x. So here the whole function derived with regard to x is 6, and with regard to y it is also 6 in this case. Okay, so basically that's how automatic differentiation works in reverse mode. Questions so far? So if you are asked ever to implement automatic differentiation in reverse mode. So I was looking into research, into literature, and did not find anything. So that's why I'm proud of the next slide, because like I added this slide to every Wikipedia article that exists. And this is actually the schema you need. If you want ever to implement automatic differentiation, and by the way, reverse mode automatic differentiation is basically the foundation for back propagation in neural networks also, because like actually what you do in reverse mode is the same technique as you use for back propagation of neural networks, just using more complex functions. So this is actually the blueprint for implementing automatic differentiation. So the idea is, okay, like you should know, like you have the expression here, and I implemented this inside of a database system. So the idea is, okay, I get an abstract syntax tree of this expression as input. So you should know that the input basically is just an abstract syntax tree of this expression. And then I'm parsing this expression. So like the first thing I can see, can't read my own typesetting anymore. Sorry. So the first thing I see is the multiplication. So you should see a multiplication. So you can see two parts, the left side and the right side. Okay, and that's what I do. Here, the C actually is the abstract syntax tree as input. So what you can see is, okay, I have a multiplication. So this is the case for I'm reaching in the first time. So I have my A. My A is actually x plus y, and I have my B, which is actually z. And then I recursively call the algorithm. So I call this algorithm again onto the left side and onto the right side. So here on the right side you see the example. So first I call this function, and then I have to recursively call it only for x plus y and only for z, because I have 2 times the call to derive. So here you see 2 times the call to derive. And remember the seed. So the seed is always the partial derivative you're propagating. And also attached is always the seed. Like here, the first time was like a times b, and what we do is like the original c by the evaluated statement of b. So so basically we had x plus y times z, and therefore for the left side x plus y would be 5 and z was 6. So we once call it with 6 and once with 5. Okay, and then again we can see, for example, for the left side, for the right side. Let's start with the right side. Like the right side, we had the set here, so we have only a variable. So we reached this case. Then we can say, okay, actually the seed value is the derivative. So now we have computed the first derivative. And in this case, okay, so z actually is 6. So we have computed like the first one already here. So we know that the whole function derived with regard to z is 5. For the other side, it's just a plus b. Or in this case, x plus y. So we're having this statement, and then we can just use the seed, so the second argument, as a derivative. So here we have the seed, and therefore we also computed the derivatives for x and y. So for x, like the whole function with regard to x is 6, and also with regard to y it's also 6. Okay, so that's actually how I explain reverse mode automatic differentiation. And if you ever want to implement automatic differentiation, you should know that you have to go through the expressions and then recursively call the algorithm. And here you see how I implemented it within the database system Umbra. So I had my expressions, like here, where is it? I had this information unit, this was the expression, and I had my value, which I'm using as seed, and that's how I implemented in a database system. So it's just to better understand the pseudocode, I have included this C++ code at the bottom. Okay, questions? If it's not the case, I can explain also forward mode automatic differentiation. and basically we have always determined first the independent input variable we want to get the derivative for. So for example, if we have the same function and now we want to compute it with regard to x, so we also have to compute the derivative and evaluate the expression in the same path. So we first just we evaluate the function, so it's 2 plus 3, it's 5, and in the same path we need the derivatives for addition, and it's also just the addition of the derivatives, it's 1, and then we also need the derivatives for the multiplication, and this is 6, and we end up by the same result, so the whole function derived with regard to x is 6. But that's how the forward mode works. And I can also show you the pseudocode. Like here you can see for the variable, the one which is currently the one we want to derive for, we return 1, and for all the other ones we return 0. And then, if it's not a variable, we have to evaluate. So in the first the first element of the pair is the evaluation, and the second argument of the pair is the derivative. So we need to implement all the derivatives for each binary operation, and then we can run the algorithm again. So here we have our algorithm, and first we have to evaluate the inner part. We start with the outer one. So x plus y and z and x. So the derivative of z with regard to x is of course 0. This one has to we have to dive further into this statement. So we first have to evaluate x. We return 2 and 3, which is the actual value, and the derivative of x with regard to x is 1. So then we can evaluate x plus y. This is 5. And the derivative, we can look it up here, is actually the addition of both derivatives here. So it's just a second value of the pair, so it's 1 plus 0. And then we can also do the same for the multiplication. And here the formula for the multiplication is actually the derivative of a times b plus a times the derivative of b. So here we can compute it. So it's actually the derivative of a. So of the first, that is actually 1 here, times the value of the second, and then we take the value of the first one times the derivative of the second, and we receive the the total result, which is 5 for the value and 6 for the derivative. Yeah, so that's actually how forward mode automatic differentiation works. So if one ever asks you how it works, you have seen it right now. Okay, questions? If it's not the case, I will show you how you can use how you can represent matrices in SQL. And the idea was, okay, I have my matrix, which normally would look like this. And then how can I implement it in a table, as a database table, either each line by 1. So here you have the row number, and here the column number, and here you have the values. And instead you can have a coordinate relational representation. So one reviewer was angry about the name. He said it should be named coordinate relational representation. Coordinate relational representation, where I have my indices here, x and y, and the value as third argument. Okay, so now the question is, how can I transform my tabular representation into my relational representation? And I'm showing you this using the iris dataset. So the iris dataset is actually a toy dataset. So it's actually a really old dataset. And it can be used for classification because like you have 3 kinds of flowers, like 3 kinds of iris, and so setosa, versicolor and virginica, and they differ by the petal and the sepal, either length or width. So how long they are and how broad they are, and you have all the numbers. It's a small data set, 150 tuples, and as an example we can use it right now. And what I did is I have my table here, my 150 data points, and then I want to have the I want to get the species here, which is actually the classification, and I need one hot encoding for that. I want to have, okay, I have 3 classes, and therefore if it's the first class, the first number should be 1, and otherwise the last number should be 1. And the other 4 attributes should be stored in another matrix. So I can do this. I first have to create my table. And then for every attribute, I have to encode it into a certain row. So the first, second, third, and fourth. And now the question is about the one hot encoding. Who knows one hot encoding? 1, 2, 3. Okay. Never mind, because like I'm explaining it anyway. Like the idea is, okay, I have normally my classes like setosa, versicolor, and virginica. And the idea is, okay, instead I want to have a vector which is 1 at one point. So one hot encoding means instead of having a name for the classes, I have only a vector which is 1. For example, setosa should be a vector with the first entry is 1, versicolor should be a vector with the second element being 1, and virginica should be 1 with 1 at the last one. And basically when I'm having a machine learning function, the idea is like I get a vector with some probabilities, and at the end the one with the highest probability is actually the class, and therefore I have my label at the end, which is actually my one hot encoding, and I have my my model, which is actually a vector of probabilities. And then I can say, okay, I measure the difference for the error, so the loss, how much my model is wrong. And therefore in the first step, now here, I want to show you how can we do a one hot encoding using SQL. And I did it, and like you can see here. At first I created a dictionary. So I said, okay, I want for each each class, I want to have a certain row number. And I do this quite simply using a distinct statement which returns me all the classes I have. Oh, I need power, sorry. I'm running out of battery. Okay. Is it working? Yeah, it is working. Okay, so in the so here I create my dictionary, and I'm doing this quite easily just using row number with a window function. And then the idea is, okay, I'm using this row number here to substitute the class here, the string, by a certain row number. Okay, but then I'm having instead of the one hot encoded vector, I still have only a number here at the end. So here I have my number 1, 2, 3. So now in the next step, I want to get to one hot encoding. So what I do actually is the row number here is actually used. So it's a bit of a trick of mine. So like the row number is used as the matrix entry. So I have my matrix, And then at the point where it should be 1 is actually the entry, and I'm doing this like here. I'm using the row number here. So no, that was the original row number, and I'm using here the rank I created here. I'm using this as the second dimension. So I have here my row number, my original row number, and the first attribute, and the rank here as the second attribute. And what I do at the end, I have a lot of 1s here, and that is my one-hot encoding. And so what I can do then is I can do a right outer join where I substitute all the values that do not exist by 0, and I have my one. I have created a dense matrix, also including the 0 entries. Okay. So that's actually how we can do one-hot encoding in SQL. So, and by the way, generate series is quite useful. So what I do here is like I use generate series to create for every dimension. So like this is the J dimension. So like here, this is the This is the J dimension here. Is it? And this is the other dimension. Here. Yeah. Okay. And now the question is how I can have my remaining matrix operations in SQL. So basically creating the matrix is just a create table statement, and using the representation I have shown to you, I can do a single matrix multiplication. So quite simply by using the indices. Like, okay, I'm joining my two tables, and I can because like a matrix multiplication is just the sum over element-wise multiplication. So I can use an aggregate function for the element-wise multiplication, and this is my matrix multiplication in SQL. I have my sum of inner products, and that's what I do here. And this is quite easily can be done with the indices I have in my coordinate relation representation. Harder multiplication is the element-wise multiplication. It's quite simple. And then in machine learning to calculate the loss, you have the sigmoid function, which is also easy in SQL. And transposing a matrix is just renaming the indices. Okay, so you see, with a coordinate relational representation, you can quite easily deal with SQL. Okay, now you have seen basic automatic differentiation, and you have seen matrix algebra in SQL, and now we can put this together. And the idea is, okay, instead in machine learning, I'm having matrices that are, so weight matrices that are multiplied with each other to, which should approximate the one-hot encoded vector. And actually I'm doing this, I have my function here, I have my original input data, I have a weight matrix, afterwards I have my model applied and so on, and that's actually my model. And here at the end I'm subtracting my one-hot encoded labels with the model to calculate the loss. And I did it so you remember the recursive statement in the beginning for gradient descent, and basically that's the same but for arrays. And here you can see automatic differentiation on arrays. So how does it actually work? So here this is actually the same graph just for applied to a two-layer neural network, and then we can do back propagation, which is actually the extension of reverse mode automatic differentiation, and then we can calculate. We have also our derivatives, so we know them in advance. So there's a book where you can have them, and that's how we can apply it for every layer, and we can get the derivatives for all weights. And at the end, we would end up with one big recursive statement where we have the initial weights, and then we calculate for every layer the partial derivatives. Yeah, it's just of a bit of what my research is, and getting this fast. Okay, questions? So I won't ask this in the exam, but I wanted to show you. So of course you should have a basic understanding about automatic differentiation, but actually I think in the exam, so of course I will ask about recursive CTEs. There will be a question on recursive CTEs. I'm not sure whether there will be a short question on k-means. I don't think so, but maybe there is. But also how you can do all the matrix multiplications in SQL, I'm not sure whether this I'm asking. So you do not need to know such statements on your own, but I wanted to include it in the lecture just to see what I'm doing, as this is my research, and basically it builds up on what you have learned in the previous classes. And also, machine learning is so popular and no one knows how to implement automatic differentiation, and I'm so proud of it, so I wanted to show you how it works. Okay, if there are no questions anymore, I would say we have 50 minutes of a break. So on my clock, the clock, no, it is still not going correctly. So on my clock this would be 5:40. So we meet again at 5:40. See you later.